I'm going to talk today about the combined solutions of the RD anomalies or RD stars anomalies and the dark matter problem within a framework that involves Leptoquark. So this work has been initiated into the 2019 Lizouche workshop on physics at the TV working group, new physics working group, and it's involved with many people from many places around the world. So it just appeared like 2 weeks ago. Okay, so what about the motivation? The first motivation, of course, is the flavor anomalies, because we know there are some anomalies between which point to the violation of lepton flavor universality in the B meson decays. And basically we have so many kind of solutions, not so many, but actually 3 appealings basically based on Leptoquarks. But actually in our work, in this work, we are only interested by the models actually that can address the RD star. So basically you can only extend the standard model with 1 Leptoquark species, which is a singlet under the SU2 gauge group. Okay, the second motivation is dark matter, because we know there are dark matter, but only from gravitational evidence. We cannot have, there is no signal at high energy colliders or direct detection, indirect detection experiments. Basically, there are a lot of mechanisms that can give rise to the correct relic density, but the problem is how to test them. So in this model, actually, we can have the correct relic density, or not only through freeze out, but also through the conversion driven freeze out, which is called co-scheduling mechanism. Okay, and the third motivation is, of course, grand unification, because whenever you have grand unification theory, we will have also leptoquarks in the spectrum of the particles. Okay, so the model is very simple. We extend with one scalar leptoquark, which is even under Z2 symmetry, and this Z2 symmetry is used to stabilize dark matter candidate, which is chi0 dark matter candidates, and then we have a chi1, which is the partner. Basically, the interaction is written in this form, and we have the third term. It is relevant for dark matter interaction, while the first and the second one can be used actually to solve the anomaly, and of course have so many collider implications. Now, of course, we have many parameters. So lambda R and lambda L are actually 3 by 3 matrices, and if we assume that the entries are real numbers, basically we have 18 free parameters. Actually, not all of them are relevant, but only actually we found out that only 2 of them are relevant. So these are lambda L, the 3 by 3 entry of lambda L matrix, and the 2 by 3 metric entry of the lambda R matrix. Okay, so we do not demand only that the RD star anomalies are addressed, but also a bunch of other measurements. Okay, so this are the kind of the results that are projected in the plane of lambda L and lambda R, but basically they are dependent on the mass of the leptoquark, and this blue lines actually correspond to the differential ratio of the leptoquark going to tau plus C, okay, plus charm quark. Okay, so we have to define benchmark scenarios or benchmark slope in order to discuss the phenomenology. As I mentioned, so this lambda depends on the mass of the leptoquark, so we have to define a benchmark slope, which is identified by this BS plus 1 number, which is defined as slope. Then we have another Latin character that basically define the scenario and is identified by the mass of the leptoquark. So we can have BS1, A or B or C, depending on the mass of the leptoquark. 1 and 2 actually, so the 1 is dominated by the left-handed components, and the 2 is dominated by the right-handed components, and they give rise to different phenomenologies. Okay. Okay, so here are some characteristics of the benchmark scenarios and the benchmark slopes. So of course the production cross-section, we have 3 channels, basically the partner pair production at the LHC, then we have the single leptoquark production, which is only relevant in association with a tau lepton, because we cannot have a top quark in the in the proton, and also the bottom quark has a very small contribution. And then we have leptoquark pair production, and so of course they do depend on the mass of the leptoquark and so on. So we use the leading order calculations for the matrix elements because we have to somehow only have like kind of conservative estimates of the bounds of the LHC bounds. Okay, so for the decay, we have different decay channels. Basically, the Chi1, which is the partner of the dark matter, only have 3-body decay. While for the leptoquark, of course, it decays to a quark plus a lepton. But if it's kinematically allowed, and in the same time, if the coupling is quite large, so we can have a dark decay, okay? And so this dark decay, of course, depends on the mass placed in between the Chi1 and Chi0. Okay, so from this, we have 3 relevant searches. Of actually 3 categories of searches. We have the missing energy searches. Basically, this stem from the production of the pair production of the partners. And then we have 3-body decay to dark matter plus either hard or soft object. So that leads to monojet, soft lepton, multi-jet, tau plus met, and so on and so forth. Then we have leptoquark searches. So this basically either a single leptoquark production or leptoquark pair production, and we have different final state signatures. And the third one, which is more interesting because it connects the Flavour anomalies with dark matter directly, because we have resonant leptoquark plus met. So in this case, we have leptoquark pair production. One of them will decay invisibly or to dark matter plus soft object, and the other one will decay to a quark and lepton. So we have a resonant leptoquark that is reconstructed from the quark and lepton and a very large missing energy. And this is very correlated to the Flavour anomalies. Okay, so here are the limits, and basically we have the met searches. So basically I don't have so much time, so I have to run very quickly. So basically we have 2 regimes, one when delta larger than the mass of the B, or when smaller than the mass of the B. So if it's smaller than the mass of the B, we have only long-lived signatures, and which is we don't use in this analysis. So we focus on the regime where delta, which is the mass placing between Chi1 and dark matter, to be larger than the mass of the B quark. Okay, so here are some exclusions. So for BS1, the constraints are much stronger, while for BS2, we have relaxation of the constraints. For leptoquark pair production and single leptoquark is not very sensitive, so we can have down to 440 GeV depending on the coupling, while for leptoquark pair production, we use it to constrain the product of the branching ratios. Resonant leptoquark searches, there is only one search used by CMS, so it's C mu plus missing energy. And basically for the scenario we use in our study, this is very small because the muon is only coming from tau decay, so it's softer, and therefore it doesn't constrain the model. So we have identified some scenarios where we can use, instead of C plus mu, we can use C plus tau or tau plus tau. So this can motivate new searches in the new run of the LHC.
You have 1 minute to go.
Okay. For direct detection, it's only through one loop diagrams, so it's expected that it doesn't go into constrain the model, and also it doesn't depend on the benchmark scenario because it's only it's dominated by the exchange of the gluons. Okay, so we don't have so much sensitivity from the direct detection. While for the relic density, we have 2 regimes basically. So if results, it is either we have annihilation, self-annihilation, to a pair of leptoquark, then we produce 4 fermions, or we have a co-annihilation that produce resonant leptoquark, which decay to either C tau or tau or B nu, depending on the scenario. Then we have the co-scattering mechanism, where the correct relic density is produced from the transformation of Chi1 to Chi0, or the self-annihilation of Chi1. Okay, so here is kind of a plot that identifies the different regions depending on the kinematical regime. For the summary of the result, I have these many plots, but basically I don't have enough time to discuss it. Also the other one for BIS2, I don't have enough time because it's a very busy one. So these are the benchmark scenarios for future searches. We identified new for benchmark scenarios that actually can be interesting for the future. And thanks.